Alrighty, so picking up where we left off, I'm going to accelerate one of you to approximately 300 million meters per second, which is approximately the speed of light. And I'm going to use the sun instead of the earth. This person is dropping towards the earth, but imagine yourself dropping towards the sun. You'll be falling into the sun if you're my volunteer. I'm going to drop you off from approximately the Parker Sun probe, which is, it's actually 6.5957, but we're going to use 6.957 times 10 to the ninth. And I need to find the acceleration due to the sun to get you up to the speed of light. And I'm going to use this A is equal to G times mass of the sun divided by D squared, which we found together in our homework. We plug in, this is for G, and we get, G comes with a bunch of its own units, and we put the top ones on the top and the bottom ones on the bottom. And so this is our gravitational constant. In fact, let's look, the gravitational constant, let's look up the gravitational constant. All right. So the gravitational constant, this is the number part, which we got correctly. This is m times m times m, which goes on the top. Negative means it goes on the bottom. This is kilogram, and this is seconds squared on the bottom. So it's m times m times m on the top for the units. On the bottom, it's kilograms times seconds squared. Okay. So that's how I got these units and these units. And then the mass of the sun is here, 1.989 times 10 to the 30th kilograms. And then the distance between them squared is going to be 6.957 times 10 to the ninth. 6.957 times 10 to the ninth. Now that has to be squared. So because this was in meters, 6.957 times 10 to the ninth, it would have been a little m inside here, and that meters would have been squared. So I moved it outside, but when I moved it outside, I had to move the square outside, which is m times m. That's why there's two m's down here. Okay, so if I have something on the top and something on the bottom, I can cancel them out. So I cancel out these m's. I can only cancel out the ones that I have on the top and the bottom, so I'm left with an m. I have a kilogram on the top and a kilogram on the bottom. So now I'm left with meters per second squared. Meters per second squared. So that's good, because I know that those are the units that I measure acceleration in. All right, everything's going to be okay. So we so we plug that in, and we get once. And that was, so this was the part that was the units part. I needed Zara to correct me for, and the other part I needed correction from Glenn. So that ended out with 2.74 meters per second squared for our acceleration. And then I lead you through in our little text here a little thing about v final is the velocity you started at, where we started, plus the acceleration times time. So v final, the velocity when you started, we dropped you off, you were at 0. So this goes to 0, so that means your final velocity is equal to acceleration times time. And we know your final velocity is the speed of light divided by the acceleration, which will equal time. You can eliminate everything here except one of these s's because it's divide by, you move it to the top. So you end up with, oh, I didn't put the unit there to insert a comment. I don't know how to insert a comment. There we go. I need to take off my own grade for not doing units here. All right. So we get 109,305,930.13 seconds. So it seems like a really long time, but it's a little over 3.466 years, definitely not an infinitely long time. And after that, you are exceeding the speed of light. You would be going faster than light. We know that nothing can go faster than the speed of light. There is a problem here, however. So we found out that we're falling for a little over 3 years, right? There's a problem here. We're going to figure out that problem when we get to our Robbie the Robot, which is my next video to put out for you guys. And that has to do with, did I hit the sun before I got to the speed of light or not? So we will cover that in our next video, but before that, let me tell you about the second part of part 1, which was thinking like Dirac, not related to the first part about gravity. So we have this equation, E, which is energy, is equal to 1/2 the mass times the velocity squared. I know it's really annoying that sometimes this little m is a unit for meters and sometimes this little m means mass, and I'm very sorry. But in this case it means mass. So for your homework you needed to solve for V. So let's pull up Paint. All right, and I need to get one of those things where I can, all right, so E, oh, right, here we go. No, that's not big enough. E is equal to 1/2 mv squared. I'm going to multiply both sides by 2. When I do, on this side, I get 2 over 2, and I can eliminate both of those. And here I get 2e. So 2 times the energy is equal to mv squared. All right. So now I'm going to divide both sides by m. I can eliminate this and this because they're on the top and the bottom. And now I get that leaves me with 2e over m on one side is equal to v squared on the other side. And I can take the square root of both sides and I get 2e over m, all under the square root, is equal to v. Sorry, a little glitch there, and I'm going to continue this in the next video, but I end up with this on the square root side, or this under the radical, which means I have to take the square root here, and I've taken a square root on this side. Now when you take a square root, when I take the square root of v squared, I should come up with a plus and a minus, because I took the square root of this side and I took the square root of this side, and when I come up with an answer from taking a square root, there's a positive answer and a negative answer. All right, next video we'll wrap this all up.